Millions of miles of physical fiber optic cables connect the world's computers. But a physical connection alone cannot deliver data to a specific software application. Without a logical addressing system, raw data pulses are indistinguishable from electrical noise. To solve this routing problem, network architecture divides communication responsibilities into distinct, overlapping layers. For data delivery, the two most critical are Layer 3, the network layer, which moves data between host machines, and Layer 4, the transport layer, which delivers that data to the correct logical process. We are going to construct the journey of a single data packet from first principles, examining how it is multiplexed, addressed, and algorithmically routed to survive transit across the internet. Without these logical layers working in tandem, global internet communication would collapse into an undeliverable barrage of raw data. Before a host sends data, it requires an application address, multiplexing. A data payload is wrapped in a transport layer header, identifying a 16-bit source and destination port. These logical channels direct traffic into specific software processes. The simplest method is UDP, forming a fixed 8-byte block. UDP is connectionless. It has no flow control or error checking and offers no guarantees that a packet will reach its destination. It simply labels the data with a port and fires it onto the network. This lack of overhead makes UDP the standard protocol for voice-over IP, online multiplayer gaming, and DNS queries. When raw speed is more critical than packet-perfect accuracy, engineers choose UDP, accepting potential data loss to ensure real-time streams do not buffer. When guaranteed ordered data delivery is required, the network uses the Transmission Control Protocol, or TCP. In this diagram, the transport header expands up to 60 bytes to accommodate sequence numbers, acknowledgements, and control flags. Unlike UDP, TCP is connection-oriented. It requires a specific setup phase between the client and server before any application data is transmitted. This is the three-way handshake. First, the client sets a SYN flag and sends a sequence number. Second, the server acknowledges the request, returning its own SYN flag and an acknowledgement number. Finally, the client sends an ACK packet back. The two-way connection is established. TCP also establishes flow control through a 16-bit window size field. This determines available buffer space, preventing a high-speed sender from overwhelming a receiver's capacity. The latency of a three-way handshake is the architectural requirement for achieving guaranteed, loss-tolerant data transmission across an unstable network. Once the transport packet is formed, it moves to Layer 3, the network layer. Here, the data must receive a host-to-host delivery address. The original IPv4 standard used 32-bit addresses split into rigid classes. This was inefficient, wasting thousands of addresses and accelerating IPv4 exhaustion. The solution was CIDR. The address shifts to CIDR notation, slicing exactly 27 bits for the network, allocating blocks based on specific need. This flexibility enabled subnetting, dividing a large network into smaller subunits, as well as supernetting, which aggregates multiple routes to simplify routing tables. Both techniques manipulate the CIDR prefix to manage network traffic more efficiently. By optimizing how we group and locate physical machines, the shift to CIDR prevented the internet from collapsing under IPv4 scarcity.
Despite CIDR's efficiency, the volume of modern devices eventually exceeded the mathematical limits of a 32-bit system. This layout highlights the scale of Internet Protocol version 6. It uses a 128-bit architecture written in 8 groups of hexadecimal digits. The IPv6 header introduces structural improvements. It uses a fixed 40-byte length to speed up router processing, removes redundant header checksums, and supports auto-configuration without a central server. With its 128-bit length, IPv6 provides 340 undecillion unique addresses. This capacity allows every device to possess a global IP, removing the need for translation workarounds. The architecture prioritizes header efficiency and direct connectivity, providing a scalable addressing system for a network that now includes billions of unique nodes. With the packet addressed, the router reads the Layer 3 IP address to forward the packet out of the local network. Routing is the process of finding the best path through a web of intermediate networks. Consider distance vector protocols like RIP. Under this model, routers calculate paths based on distance, measured in hop counts, and direction. As the diagram shows, router A only shares its routing information with its immediate neighbors. This mechanism has a limitation. Routers only know what their direct neighbors report. They update their tables based on the lowest cost, without seeing the wider map. Consequently, distance vector suffers from slow updates. Packets can get caught in routing loops, and the network can struggle to resolve paths if a link fails. While distance vector requires less processing power, its neighbor-dependent logic is often insufficient for large-scale, complex environments. Large networks use link state routing, like OSPF. Every router floods link state advertisements to all other nodes. By collecting these, every router builds an identical map of the entire network topology. Using Dijkstra's algorithm, each router calculates the shortest path to every possible destination. This complete topological knowledge eliminates routing loops and allows the network to find alternative paths immediately if a physical link fails. The trade-off is architectural complexity. Running these calculations across a full topology map requires significant CPU power and memory on the router hardware. Choosing between these protocols is a matter of engineering priorities, where architects must balance physical hardware resources against algorithmic reliability. At Layer 4, the raw data payload is encapsulated in a TCP header, which identifies the source and destination ports. Moving to Layer 3, that segment is wrapped in an IP header, receiving CIDR addresses for global positioning. The assembled packet reaches the default gateway, which uses its routing table to forward the data along the shortest path to the target host. At the destination, the machine strips the IP header, and the transport layer uses the port number to deliver the payload to the correct application. The transport layer provides the rules for process-to-process communication, managing the balance between raw speed and delivery guarantees. Meanwhile, the network layer provides host-to-host addressing, a system that has scaled from rigid classes to the massive capacity of IPv6. The Internet functions through a collaborative hierarchy of protocols. Each layer solves a unique mathematical barrier to make global communication possible.